I am explaining how to solve a linear homogeneous second order equation. What this is it's an equation where the highest differential order is a second differential. That makes a second order. Is linear since your own variable is y, and it's homogeneous because it equals 0. And this exact equation we're dealing with has three constants, a, b, and c. A times y second order, b times y to first order, and c times just y. All of this equals 0. How to solve it is you start with finding the roots of the equation. You get the roots by putting into the characteristic equation a all squared plus b all, that's supposed to be b all, plus c equals 0. And from there, you find the roots by either simplifying it or by using the equation r equals negative b plus or minus square root of b squared minus 4ac over 2a. That would get you roots, or just simplifying it can also get you roots. There are three different types of roots you can find. Well, R1 does not equal R2, R1 does equal R2, or R1 and R2 are complex with the examples being there. Well, for the first one, 1 and negative 1, 1, 1, or 1 plus I times 4. It's complex. If you have the situation where R1 does not equal R2, you can plug in your roots into this general solution. Y of t equals c1e r1t plus c2 or e2 r2t times c. You can plug in the equations there, and it'll work. And then you can solve it, which I'll get to later. If R1 and R2 are complex, you get them in the form of this. Well, R1 equals phi plus I of mu, and R2 equals phi minus I of mu. And then you can plug them into, and then you can get the Y versions of this, which is similar to the Y, similar to the, well, R1 does not equal R2, e to R1 of t. The complex version of it is e to the phi plus I of mu times t, and then same for the other one, both negative instead of plus. And then you plug that into this version of the general solution. Y of t equals c1e to 5 times t cosine mu times t plus c2 e to the 5t sine mu of t. And if R1 equals R2, you get the same equation. Y of t equals c. Y of t equals c times e to the power of negative bt over 2a, and you plug into this general solution, which is y of t equals c1e to the bt divided by 2a plus c2 times te to the power of negative bt over 2a. And once you have your general solution, you solve all of them the same way, just with different types of solutions. You solve them by taking your general solution and your initial values that you get at the beginning, and you plug in the initial values to your general solution. So for example, if I just take the standard general solution for while R1 does not equal R2, I can plug in these two fake initial equations, y of 0 equals 1 and y prime of 0 equals 2, plug in y of 0 equals 1 to the standard general solution, and plug y prime of 0 equals 2 into the derivative of the general solution. And by doing that, I get CE alt R1 times 0 plus C2 E R2 times 0 equals 1, and C1 R1 E to power of R1 times 0 plus C2 R2 E to power of R2 times 0, and that gets 2. And then solving all that, you want to solve for C1 in one and then C2 in the other, and you get something like C1 equals X or C2 equals G. And then you just plug those two variables back into your initial general solution, And that is your overall solution to the initial value problem. I'm going to do an example of this where the roots are complex. And my equation is 4y to the double prime plus 5y prime plus 3y equals 0. My roots my initial values are y is 0 equals 1, y prime is 0 equals 1. I need to solve for the initial values. I turn that into the characteristic equation 4r squared plus 5r plus 3 equals 0. And from there, I use the equation to find my roots, since I can't simplify that. And from doing all that, I get negative 5 over 8 plus I times negative square root of 23 over 8. And I plug that into my equation, my general solution. And then I try and plug in the initial values. So I plug in y0 equals negative 1 into this. And I work it out, and I eventually get C1 equals negative 1. And then I derive the general solution. I get that big mess. And I plug in y prime is 0 equals 1. And working it out, I end up with negative 1 over 5. Oh, I end up with 1 equals negative 5 times C1 plus square root of 23 C2. Since I was solve for C1, I can plug that into this equation. And so I'm able to work out from there. And the only variable I've left is C2, which I find to be 0.8 over square root of 23. I then plug in C1 and C2 into the general solution, and I get that. And I get yt equals 5 to the power of negative 5 over 8t times negative cosine square root of 23 over 8t plus 0.8 over square root of 23 sine times square root of 23 over 8t. That would be my solution to this problem. Now, the problem, if this was y1 does not equal r, or if r1 does not equal r2, this will be solved very similarly. And except with the equation here, negative 5 over 8 plus I square root of 23 over 8, let's say that's just negative 5 over 8 and square root of 23 over 8. I will instead plug that into this general solution, plug in it to R1, R2, and I will solve it the exact same way though, where I'll plug in 0 for all the t's and negative 1 for the opposite side of the equation. And I'll solve it the same way. Same as if they equal each other. If they equal each other, I would do the exact same thing again, except instead of using cosine and sine or just e2 square, I would have to use this one, which is C1 e to the power of negative bt over 2a, because that's how, if you have R1 equals R2, that's the standard form you find of the roots. Yeah, and that will be it.